Moving on to question 42, we're attempting to draw the important resonance forms to show the delocalization of charges in the following ions. In each case, indicate the major resonance forms. So it's asking us to draw our own important resonance forms, starting from a compound given. So what's the first thing I want to note? I see an electron sink here, where electrons want to flow into, and I see excess of electrons here on this carbon, which could form this double bond. So the first thing I draw is that out and then show this species. As far as indicating the major resonance forms, oxygen actually is the most electronegative element, as shown in the Pauling scale. This one. As shown on the Pauling scale, oxygen is more electronegative than carbon, therefore the oxygen has a higher propensity, chance, it has more of a likelihood to retain the electrons. Moving on to part B, we see an electron sink. I see an excess of electrons here, and I see an excess of electrons here. So what do we see? We see the electrons shift into this double bond here, and then we see this pair of electrons shift over into this double bond, allowing this pair of electrons to flow into the sink, which would again give us two double bonds on this species, and allowing the more electronegative oxygen to hold the partial negative charge. Moving on to C, we see a benzene ring, and attached to that is a methyl group, except the methyl group is, I don't know the name off the top of my head, it's been a little while since I've done this. But we're asked to show the important resonance forms and to indicate the major resonance forms. What I would say is that this is the main resonance form for a different reason. That reason being that benzene rings are just particularly stable. But to illustrate that the electrons can in fact move, we see here, this is the parent compound, and we see the electrons flow from here into this partial positive charge is effectively an electron sink. And then we see it just move throughout the compound, allowing illustrating the flow of electrons throughout the compound. And then I made a mistake because I'm dyslexic, and I skipped to question E, which is paired funnily in this textbook. And we see this species, so I didn't draw the hydrogen, but from line angle structure, whatever they call it now, we can pretend it's here. It's imagined, it's implied that it's there. What do we see first? We see an electron sink. I see an electron donor / sink. I see a pair of excess electrons. So what do I see here? We can see the electrons can flow into this oxygen, and the electrons can flow into the partial positive charge here on this carbonyl, this aldehyde species, and this lone pair can also donate its electrons into this double bond. The problem with that, though, is that while it would allow this oxygen to hold the partial negative charge, and this nitrogen also is okay to hold the partial positive charge. This structure actually just entirely does not include a negative or a positive charge on any atom. Therefore, it is the most stable of the two possible forms. Now, skipping back to D, what do we see? We see an electron sink in the form of this partial positive charge. We see electrons adjacent to it, which allow it to flow into it. And then we see more electrons adjacent, which allows it to flow into the sink that would be created here. This is illustrated here, where my most important resonance form would likely be here because both double bonds are allowed to donate into this sink. So this would be the most important resonance form. It would show up the most. However, there is a case to be said about these two conjugated double bonds. For the purposes of your instructor, I don't think that would be too important. Moving on to F, we see, what do I see? I see two pairs of electrons here. I see an electron-rich double bond, and I see an electron sink in the form of this partial positive charge. You see them using the same exact words over and over again. So what do we see? We see this electron-rich double bond donating its pair of electrons into this partial positive charge. That would normally create a vacuum where the nitrogen would be. I don't like that. That would normally create a vacuum where the nitrogen would be adjacent to the nitrogen, but this is also allowed to donate its pair of double bonds into this, the adjacent carbon, which would retain the partial positive charge. This would be the preferred species because nitrogen, I forget the reason. I want to say it's because carbon likes 4 bonds. As a general rule, carbon likes 4 bonds. Oh, nitrogen is also bigger. Nitrogen is bigger, which allows it has more protons in its nucleus, which allows it to better hold a positive charge because it's simply further away from the nucleus. So moving on to question G. I see an electron-rich species in this oxygen. I see an electron-rich double bond here, and I see another electron sink in the form of this partial positive, positive charge. So what do we see? We see electrons move from the double bond into the sink and from the oxygen to stabilize the positive charge that would otherwise be left right here, where the double bond used to be, allowing this structure. This structure would be our major resonance form. I'm going to question H. I have an electron-rich carbon. I have an electron-rich double bond, and I have an electron-rich oxygen. So what we can draw is the electrons flowing from this carbon here into the to form a double bond here. This double bond to move over into here, forming a double bond here, and this double bond flowing into the oxygen, the most electronegative atom, which could better retain the double bond, the electrons. This would then be the most important resonance forms. It would be the most stable among the two forms. Moving on to I see CH2 double bonded, which is electron rich. I see another electron rich double bond, and then I see an electron sink in the form of this positive charge. And I see, I forgot about the end. So we can draw slowly, sequentially, with one arrow, the electrons flowing into the sink, relocating the positive charge in between the two double bonds. That leads me to think that this would be the most important resonance structure because both double bonds can donate its electrons to fill the sink. And we can take it one step further and move these electrons from this double bond over, leaving the partial positive charge on the tail end of the compound. Moving on to J, I see an electron-rich double bond, I see another electron-rich double bond, and I see a partial positive sink. However, in this case, I also see two hydrogens here inhibiting the flow of electrons, as also illustrated here. So this would actually just not have resonance structure, period, just because of these two hydrogens. It's important to note that. Moving on to K, I see an electron-rich sink. I see an electron-rich oxygen. I see electron-rich double bond. And, oh, there might be an issue here. I don't see, I suppose it has two, there might be an issue with this compound. It should have double bond here. So let's just draw this out really quickly, because I think there's a problem with that question. What question is this? 41? 42? So moving on to my drawing pad. Let's try and draw it out, because that is kind of funny. So I see CH2, I see a single bond, and this is partially positive. And then I see CH, this is attached to a double bond, which is attached to a CH, which is attached to an oxygen, which is rich in electrons, and then I see a CH. And then I see a CH2. What would I suggest? There's an issue with this compound in the way that this carbon only has 3 bonds attached to it, which would indicate it's a partially positive charge. You can see that here too, where this carbon has 3 bonds associated to it, one to each hydrogen. But that's not illustrated in this textbook for some reason. I can't reason why. I do think it's a mistake on the part. It's a mistake on somebody, because it's not indicated as a double bond either. If it was a double bond, which is the way that I drew it over on the right here, I drew it in as a double bond, imagining that that would be correct. I'll illustrate my example. So my example, I drew the exact same structure, but I drew it with a double bond here instead of this single bond, which shouldn't exist in the compound. It's missing electrons, and it's not indicated anywhere. Very odd. So I'll pretend that there's a double bond here, and I'll save this question for later. But we see the electrons flow from this double bond into this sink. leaving behind a partial positive charge, as also illustrated here. And then this oxygen can donate its electrons to fill the double bond, which would leave behind a partial positive charge on the oxygen. And then I drew this double bond donating into this double bond, to form a double bond here. However, you have to also expel this double bond and pump it back into this carbon on the end, because oxygen would then have 4 bonds attached to it, which is too much. Forming this structure, but I'm beginning to think that these structures are just never going to happen in solution. K I'll have to probably look at it again another time, but that's